Welcome everyone, I am Praveen. I am one of the TAs for this course. In this video, pool boiling experiments are demonstrated. You might have seen boiling of water in a pan or in an electrical kettle. However, through these experiments, we will get a closer look towards the different regimes of pool boiling, and you will also get an idea of the heat transfer capability of boiling phenomena. The pioneering work on boiling was done by Nukiyama in 1934. He conducted pool boiling experiments using nichrome and platinum wires immersed in water, and he could observe 4 different regimes. The first regime is natural convection boiling, and the second one is nucleate boiling, and the third one is transition boiling, and the fourth regime is film boiling regime. And he also plotted the pool boiling curve, which is shown in your manual. You can see the boiling curve here. He plotted the same kind of curve based on the different bubble dynamics in different regimes. In natural convection boiling, we do not see any formation of bubbles, although the heat flux is increased. This is because to form a bubble we need some initial superheat. So, before the superheat is achieved, I will see only the natural convection boiling, where we do not see any bubbles, but heat is transferred through the natural convection. As we increase the heat flux, we can see the formation of small bubbles, which is the regime A to B here. We see small bubbles forming, and but these bubbles collapse when they reach above the surface, boiling surface. When we further increase the heat flux, we will see some column kind of bubbles which are vapor slugs. These bubbles reach up, and they release the heat through the evaporation, and they release enormous amount of heat because of their capability to transfer latent heat. And if we further increase the heat flux, most of the heater surface is covered with the vapor bubbles, and these vapor act as kind of insulation and reduce the heat transfer, and this the downward increase you can see the curve here. This is the transition boiling regime, where most of the heater surface is covered with the vapor. And if we further increase the heat flux, we will observe a stable vapor film formation, and again the heat flux increases. It is because of the domination of radiation. And the maximum heat flux that we can safely achieve is the point C here, which is the critical heat flux. In the heater controlled boiling experiments, where we control the heat flux, we generally do not see the downward increase of this curve, and once critical heat flux is reached, we directly go to the melting point E, where the heater surface melts, and this should be avoided to prevent any thermal failures. We will observe these regimes in this experiment. The experimental setup is shown in your manual. It looks like this. The one in your manual shows the pool boiling chamber in which the liquid is filled. The second one is the water cooled condenser through which the cooling water is supplied, and this helps in maintaining the constant pressure even though we boil and even though the formation of vapor occurs. The third one is the cylindrical surface on which the boiling takes place, and the fourth one here it is the water flow meter, through which we can adjust the flow rate through the condenser. And the fifth one is the chamber pressure gauge. It shows the gauge pressure inside this pool boiling chamber. And the sixth one here, it is the charging or the drain valve, which helps us in filling the liquid or which helps in draining the liquid. And the seventh one, it is behind this, which is the air vent valve. It helps us in removing any air if present. And the eighth one here, it is the watt meter, which helps us in controlling the input heat flux given to the boiling surface. And the ninth one is the knob here, which we can control the heat flux. And the 10th one is the switch. And the temperatures, we measure 5 temperatures as shown in your manual. The T1 here, the T1 shows the temperature of the heated surface, whereas the T2, it measures the liquid temperature. 4 thermocouples are inside this chamber, and The other thermocouples are in the valves of water cooled condenser. The third one, it shows the vapor temperature around this water cooled condenser, and the 4 and 5 indicates the temperatures of the water coming in and water coming out of the condenser. And you can measure these temperatures through the panel here. The knob here shows the temperatures. If you turn the knob, then you can here it is showing the T1, which is the solid cylinder surface temperature. It is around 25. We are not heating, so, and if you rotate the knob, you will get the T2, which is the liquid temperature. Now it is around 24, and T3 is the vapor temperature, which is around that water cooled condenser. It is around some 23, and T4 and T5 are the inlet and outlet temperatures of the water flowing through that cooled condenser. These are the temperature measurements you will have in this experiment. The procedure is simple. First, check whether the gauge pressure is corresponding to the saturation temperature of the vapor here, that is T2. Here the temperature is 24, and we use the working fluid SCS36, which is a refrigerant. We have chosen this fluid because it has a saturation temperature of 35 degrees at atmospheric pressure. In case of water, it requires 100 degrees to evaporate. So we use this refrigerant so that we can boil this refrigerant at small amount of heat fluxes. First, check before proceeding, you can check the saturation pressure, whether the gauge pressure is corresponding to the saturation pressure of T2. The T2 is 24 degrees, and the saturation pressure of SCS36 is listed in the properties in your manual. It is around some 0.7 and 0.6. So here it shows the gauge pressure, so you subtract atmospheric pressure from this. This is the heater controller. You can increase the heat input given to the cylinder. Let us say we can keep some 10 watt. You slowly increase the heater temperature. Now the heat input is around 12 watt, and you can see the bubbles forming. This is kind of nucleate boiling regime, where the bubbles form and they release heat through the evaporation and boiling, and the evaporated vapor is condensed here, and you can see the liquid dripping from the water cooled condenser. This condenser helps in maintaining the saturation pressure, and also it conserves the mass, so that the same amount of liquid always stays in the pool boiling chamber. And if we can slowly increase so that we can observe the different regimes. However, we have to take the steady state measurements, and it usually takes some 10 to 15 minutes to reach steady state. However, due to the time limitation, we can increase the heat so that you can observe different regimes. I am slowly increasing the heat input. Now I have increased to around some 43 watt. Now you can see the rigorous boiling compared to the earlier regime. This is still in the nucleate boiling regime. You can also measure the temperature of the surface. Now the temperature of the surface is around 35 degrees, and the pressure is some 0.7 bar, that is the absolute pressure. we increase the heat flux, the surface temperature increases, and this setup has designed so that it could reach only up to 160 degrees, because beyond the temperature the critical heat flux reaches and the solid gets melted. So, in order to prevent the thermal failure, there is a temperature controller here which stops the heater if the surface temperature reaches 160 degrees. You can take similar readings and plot the pool boiling curve as given in your manual. You can slowly increase the heat input. Now, I have increased heat input to 120 watt, and the surface temperature is also increased to 38, and you can see the rigorous boiling phenomena occurring in the boiling chamber. This is in nucleate boiling regime. Still we haven't reached critical heat flux. Usually you should wait till the steady state is reached, but it takes a lot of time. For each heat flux, it takes around some 10 to 15 minutes for the steady state to be reached. So, we are skipping that due to the time limitation, and I am increasing the heat input. I have set heat input to 235 watt, which is near to the critical heat flux for this working fluid, and you can see most of the cylindrical surface is covered with vapor formation, and the surface temperature also increased from 38 to 55 degrees, which is around some 20 degree jump, and if I further increase, it will reach to higher temperature, and the controller here it automatically shuts down the heater in order to prevent the thermal failure. And you can see the resigns which is near to critical heat flux. Still we haven't reached the critical heat flux, but we can see the heater surface, most of the heater surface covered with the vapor bubble. I am increasing the heat flux still more. And you can see enormous amount of vapor forming here, and the condenser is unable to condense. So, we can increase the flow rate using this valve. And you can also see the temperature pressure increase. So, in order to maintain constant pressure, you increase the flow rate. Now, you can see the temperature reached to 120, 168. So, the heater is automatically stopped and it is reducing to again 114. So, this is critical heat flux point. So, it is better to stop here, because to avoid thermal failure. Even though we do not stop, the controller here stops. So, this is the almost completion of the experiment. So, I am reducing the heat flux. Automatically it stopped the heater. You can see it came to 0. So, because of the critical heat flux, and the temperature also increased to 180 degrees. This is the critical heat flux point, and until now we have to plot the pool boiling curve. On y axis we take heat flux, and the x axis we take the excess temperature, which is the temperature difference between the wall or the surface minus saturation temperature. So, as we reach the critical heat flux, here I am showing the boiling regimes. These are the high speed images taken at some 2000 fps. by Georgia Tech. This is available on YouTube. I'll share the link. Here you can see the pool boiling curve. The A here show this is the nucleate boiling. This is a high speed camera. They have used high speed imaging so that they can capture the bubbles at very higher frame rates. And you can see the surface is covered with small bubbles, and the bubbles are traveling upward due to the buoyancy forces. And now the second here A to B, it includes the bubble coalescence, which is near to the critical heat flux. And now the regime near the critical heat flux, or it is approaching critical heat flux. Now you can see the most of the heater surface is covered with the vapor. And the heater surface is covered with the vapor and this is near critical heat flux, and this is the point at which critical heat flux occurs. Here you can see only the entire vapor is forming on the boiling surface. Usually people stop here once they reach critical heat flux because to avoid thermal failure. And you can plot the boiling curve. We have conducted steady state experiments that take a lot of time, but due to the time limitation I am sharing the results here. And you can plot the boiling curve as shown in the figure here, and you can also compare with the Rosenau correlation given in your manual. We will share these results with you. With this I hope you got some understanding on boiling, and thank you for listening.